Thank you very much. First, let me thank the organizer to organize such a nice and exciting and a really historical meeting. Can you hear me? Fine? Okay, good. Then, and also, thanks for inviting me to give a talk and a chance to interact with many pioneers who contribute a lot to the development of QCD. It's a really tremendous opportunities. Yeah. Then in the last 50 years, we learned a lot about QCD. We were convinced that QCD is the right theory for the strong interactions. But at the same time, there are still a lot of questions and answer the questions, mysteries about QCD waiting for us to further explore. So in my talk, I will try to focus on exploring the hadrons, the core Gluon structure, without breaking it. I will focus on the last term, so without breaking the hadrons. As you know, by breaking the hadron, we could see the quarks gluon inside. And based on George's talk, we can follow the footprints, go all the way to the final state to see in terms of the jet and the hadron form in the final state. So that's great. We learned a lot from that process by breaking the hadrons. Then, on the other hand, by feeding so much energy into the collision to break the hadron, you trigger lots of radiations. Then the radiation actually will help to explore the new QCD dynamics, but at the same time, will dilute the information, especially the correlation between the bonds, how the quarks and gluons will bond inside the protons. Those are typical, have a scale out of 1 over Fermi, but once you break it, create the tremendous radiations, then that type of information will be diluted. So that's the reason I will focus my talk on the observables about QCD, but without breaking the hadrons. So I will focus on the challenge. With a large momentum transfer in this kind of collision, you want to see the particle nature of the quarks gluon, but not breaking the proton. That's a challenge. Number two, as we never see the quarks gluon in isolation, how you match what you observe, the hadrons, to the quarks gluon inside, because that's the information you want to extract. So that's a factorizations. Then we learned a lot about factorization for inclusive process. For the exclusive process, Stan worked on a lot, but I'm going to introduce a new type of observables, exclusive, without breaking the proton, what the difficulties behind the factorization, how we overcome that. That's for the sort of for future. Then finally, as a member of a quantum collaboration, I take a couple of minutes to introduce you a new project. It's actually supported by US Department of Energy, known as SIDAC project. We try to pixelating the hadron, say proton, in terms of probability to find the quarks and the gluons inside the hadrons, inside of the momentum fraction of the protons. It's like a CT, a doctor did in the hospital, you CAT scan your brain, see the base layer of the pictures. We try to do the same to the protons. So that's what I will focus my talk. So now first, we learned a lot in last few days about QCD, which has two very important defining features. One is the confinement. We talked a lot because we still have not solved it. We still have a lot of challenge to understand the confinement. There are lots of ideas. And the consequence of that, we don't see the quark gluon in isolation, so we cannot just catch the quarks gluon to see them directly. Then on the other hand, there's another very, very important feature known as asymptotic freedom, which is so important to give us a chance to control, to calculate the dynamics at the short distance, so we can have a well-defined probe, short-distance probe, to see the dynamics of quarks gluon inside the hadrons. On the other hand, we learned in the last several days that QCD works extremely well in how these things work. Okay, QCD has been working extremely well in the asymptotic region when the momentum transfer larger than 2 GeV, say typically about 1/10 of a Fermi. At the same time, lattice gauge calculations have demonstrated they can calculate the the emerging property, bound state property like mass, spin of the hadrons. So we understand in the long distance, the QCD also work well. But I want to emphasize that most importantly for the QCD, probably most interesting, rich, and complex region of the theory is in this 2-order magnitude, known from 1/10 Fermi to 10 Fermi, say QCD at the femtoscale. Then all the emerging phenomena depend on the scale at which we probe them. So what our interest is, we want to see the quark-gluon dynamics at a short distance. But if you have a single hard-scale probe, you are no longer sensitive to the structure information. You're no longer sensitive to the size of the proton at all. So then the question is how you see the emerging phenomena of the hadron. We need a new type of probes. We need a type of observable involving 2 scales, well-defined, measured 2 scales. One larger scale to pin down the platonic degree freedom of the quarks-gluon fields, right? Then at the same time, you have a second scale, which is well measured, but is sensitive to the dynamics at order of Fermi, or a few hundred MeV or GeV. So that type of scale in this picture, you can see that imagine you have a hard collision so localized at the point, then you become the 2 scale, you not only see the large momentum transfer, which is factored into the larger longitudinal momentum, but also you have information such that you can try to pin down the transverse motion of the proton, as well as the location of the collision where the collision taking place. So that's a new type of observable. The question is the factorization, whether or not the factorization is valid. Now with this type of observable, in principle, we should be able to see the internal structure of the quarks-gluon of a bound hadron. In terms of position space, you imagine it's how the quarks-gluon distribute inside a bound state or the Fermi size, and how that distribution correlates with hadronic property, like if the proton is polarized. Those information is direct consequence of QCD dynamics. At the same time, if you measure the motion of the confined quarks, if you have confined motion, how that motion correlates with the spin directions, for example. Those are the immediate consequences of the QCD dynamics. So with this type of observable with 2 scales, we could have a chance to observe them. But there are 2 types. One is the momentum space, one is the position space. Once you break the proton, as I mentioned earlier, it triggers tremendous amount of radiations. We learned from LHC. And especially we talk about lepton hadron collider at in the US, or EIC. It's imagine you do the semi-inclusive lepton hadron scattering, a lepton scared over the proton. By large momentum transfer, you trigger a lot of radiation. What are the consequences? Consequences is that you do measure the transverse momentum of the proton at the collision point if you observe involving 2 scale, but that transverse momentum dependence is not the confining motion of the proton in the proton wave functions. The link between, of course, the QCD evolution, but the QCD evolution involving perturbative part and the non-perturbative part. So it's a challenge. My colleagues here, we have TMD collaboration, try to study this kind of confined motions. So in my talk today, we'll emphasize things not to break it. But the reason is you can see, you can do a quick estimate. By energy exchange scale Q squared at the collision energy S, the typical double logarithm will give you the order of a broadening of transverse momentum proton way over GeV. Go to LHC, it's way over GeVs. So those scale is not the scale in the confined motion inside proton wave functions. So with all this background, so now of course, rest my talk on the observable without breaking the protons. So you know the form factor, people done this many years ago. So if you measure elastic electromagnetic form factors by Fourier transform, oops. Sorry, I'm also getting confused about this. So you can measure the charge distribution inside the proton and neutron. Can we do the same for the color? Answer is no, absolutely not. There is no elastic color form factor because gluon carry color. So once a hadron, proton absorbs the gluon, then you no longer becomes a proton anymore. So what happened is that the good idea emerged a number of years ago, actually a couple of decades ago, say we can study how quarks and gluon distribute inside proton by measuring generalized form factors. Instead of exchanging a single, say, photon, electromagnetic form factor, or a single gluon, which will not happen, exchange a pair of quarks, antiquark, or two gluons in color singlet state. So in that case, you can keep the proton intact. So correspondingly, you have a matrix element, a proton come in, is scattered to the P prime by exchange a pair of protons in a color singlet state. From that, you can, by the momentum of the scattered, the diffracted, or whatever the proton, you can construct the invariant mass of the exchange state and the longitudinal momentum fraction once you choose the direction of the plus. So that this function can be in general expressed in terms of x is the momentum fraction or loop momentum between the pair and the c and the t, which is completely determined by measuring the diffracted protons. So that's a new quantity. You don't break it, but by measuring this function, you can learn something about what's inside. So then formal definition, because this is a matrix element, you can define in terms of scalar functions we call the generalized Proton distribution. I don't have pointer. Sorry. Okay, so now I show up. So they have a form factor, and then we call generalized Proton distribution H or these things. But the key is this momentum dependence. They have a C is a skewness, and if T is the invariant mass of a pair, then the X is the very important. X is the one going through your proton wave functions. So X dependence is very, very important. Then also because the relative momentum between X and the C is externally observed, you have a different region for these. If you go to extremely forward region, the operator the same as the definition of Proton distribution, can be reduced to the Proton distribution and holistic distributions. But if you're away from a forward region, then you have a different region depending on the relative size value of the X and the C. So then the question is, what do we learn by these new functions? PDF, LHC folks, friends are very interested because that's a Platonic flux, tell them how well you can see the new physics. But in this case, if you do the Fourier transform of this T, then you end up with a density distribution to find a quark in the unit of dx and dkt. So it's a special distribution of the quark density. And also with a model from Matthias Burkhardt he constructed, you can imagine this large X region, the proton look a little bit smaller, while the small X region, proton look a little bit bigger. But we don't know, we need to measure that. But because this feature gave us the opportunity to ask questions normally we could not ask. So for example, you can ask naturally, say how far does the gluon density spread away from the center of the hadron? We know the color is confined. How long the tail would be? What the probability to find the gluon density even over the Fermi? We need to measure that. That will help us to understand how the quarks gluon bond inside hadrons. And also how fast they fall. The differential shear, how fast they fall, also determined by the QCD dynamics. And also once you know this distribution, if we measured it, as a slice of different value of X, you can ask the questions, once you have a slide and the transverse distribution, what's the effective radius of the quark density to define your proton size? And the gluons. The question you can derive from that, what's the relative size between? We learned from a few days ago from lattice calculation, they prefer to have more gluon in the middle, junction picture. The heavy quark try to move away, they bounce it back from bound state. So in that case, you might conclude the effective radius of the gluon distribution in the proton is smaller than the quark. On the other hand, we know low energy quark, consider quark model, what's the gluon? The fluctuation around your valence quark. In that case, the radius of gluon effect really probably is about the same as the quark or different, but we don't know. But it is this measurement, it is this observable, gave us a chance to explore those things we could not explore once we break the proton. That's in the Platonic degree of freedom. This measurement can also give us the emerging property of the hadron itself. Start with the energy momentum tensor, then you can take the matrix element of energy momentum tensor, then you can decompose into different form factors. Then you will find that those form factors actually relate to the moment of generalized parton distribution. For example, the angular momentum of the proton spin half then projected on the longitudinal direction, then as Shantung pointed out in 97, long time ago, is exactly first moment of these generalized parton distributions. Then people also recently studied those other part of this form factor can be related to the pressure or stress force distribution inside the hadrons. So you can see, measure this kind of X dependence of the generalized parton distribution. You can construct different moment. You can make a prediction of the quantity directly connected to emerging property of your hadrons. So that's enough said about these properties. People having studied these for a while try to propose the observable to measure them. So for example, by measuring the deep virtual competence scattering, they measure the photon come to the final state from the like a DIS process, but with a diffracted proton in the final state, or meson come out, or heavy variable come out. This class of process is very unique, have the feature, the two scales. Q squared is very large, localize the collision. T is a relatively small scale. So you can have a standard two scale observable. Then also realistically, can we have this kind of event? It is one of the Herald's discovery that we can have 10 or 15% time of the Herald event with such a large momentum transfer, protons stay intact. So that gave us a chance. That's a part of the reason we try to build a EIC with a much higher luminosity, 100 to 1,000 times the luminosity, is exactly based on the event rate Herald has seen. We say how many more events we need to be able to study this kind of event. Well, for EIC, in the EIC white paper, we actually made some prediction or simulations based on the model GPDs. So you can see at a EIC, you can measure this deep virtual competence scattering as a function of a T with such nice, precise data, and you can do the Fourier transform that at different value of X. You get a special distribution. From that, you can construct the effective radius or the transverse spring R square. Then you will see the feature, the radius actually broadening. When X go to small, the system is more spread. But that all required to be measured. Then similarly for gluon from a heavy flavor, there you will find that nicely, oops. Oh, sorry. I'm still here. The forward backward, these two are not uneven when I got confused. Yeah. So you can see the gluon from the distribution, the B space, you can construct effective radius of the gluon distribution for the proton. Very nice, very beautiful. But all these based on the model we put in, whatever invented the assumed distributions. The question is, suppose you do the measurement, you measure that cross-section. How well you can do the reverse process to extract distribution as a function of X? That's very important. The answer is hard, very, very hard, at least through this type of process. I gave one example is that the deeper virtual competence scattering. Now you know, so when you integrate over X, you will find that at the leading order, the pole structure, which is not pinched, it's very simple, X equal to C. When you do the integral with the distribution, you end up with some kind of moment of distribution, and the X depends on the integral because this is amplitude, exclusive process, you work at an amplitude. Then this X dependence is fully integrated over. They are not sensitive to external scale like a Q square, all these things. So at the end of the day, you measure the cross-section. The cross-section is proportional to the moment of these distributions. It's not distribution itself. And also that moment, unlike the inclusive, we have a reason, there's more sensitive to the X dependent. We can talk at different time. But in this case, people realized, say, I can construct additional term to whatever the model you make for my GPD, so long as that term gave 0 to this moment. So as far as the X dependence is concerned, you have a completely different GPD, but as far as the experimental measurement, the DVCS is concerned, they give the same cross-section. So that additional term has a term people use called shadow GPD. So you can have infinite solution from a reverse point. By measuring cross-section, you can get, in principle, infinite number of GPD, give you the same cross-sections. Now you say, well, that's one measurement. What about other, the meson production of these? Unfortunately, all those type of process I will explain have exact same features. Does not give you that sensitive reverse information on the X dependence. So these two curves presented in this paper by Proton collaboration, you can have two GPD models are so different in orange, but at the end, they fit the same data. So that's a challenge. So what I'm going to do, let's turn back a little bit, ask ourselves, in order to understand this kind of X dependence or this kind of diffractive process, what the minimum condition you have to satisfy? So in order to keep the proton intact, you want to have the proton to be diffracted. Once the proton is diffracted, measure this momentum, then you exchange a virtual state A star with a momentum P minus P prime, quantum numbers fixed by these two hadrons. But you need a Hart probe to see the photonic feature of the inside it. So how you define a Hart probe? So imagine have a beam coming. In this case, I gave very general. A beam can be electron, can be a photon, can be a pion. So beam and collide with the state, I want the Hart scale. So I look for two final state particles, the back-to-back has large PT. So make sure the time scale of this collision is so much shorter than the lifetime of the exchange of the state. You know, if that happens, you can neglect, or as approximation, neglect the quantum interference between the collision and this hadron. So you can have chance to have factorization. So that's exactly what we say the necessary condition for this process to be able to treat in a QCD factorization approach. You require these two particles come out with a large PT, so this time is so much shorter than the lifetime of these, which is a square root of T. So this process, minimum condition, requires the two particles in the initial state, three particles in the final state. One is a hadron slightly diffracted as a function of T. Another is two back-to-back hadron. This collision flank has a large PT. So that process, my collaborator and I call single diffractive Hart exclusive process. Then you don't know what the state exchanged. It's a dashed line, I quote here, but it can be expanded depending on quantum number. It could be the virtual photon. Could be a QQ bar pair. Could be group pair. So then could be even multiple partons. But the idea is that I want the collision time so short here, pulling multiple partons here will be power suppressed. Then this is well known, if you do the DVCS, this is exactly the so-called Bethe-Heitler process. The quantum number allows you to have virtual photon exchange. So if you want to extract the two parton correlate, the GPD, you have to fight with the contribution from this term. Then also we find that if you look at the size, by exchanging a single parton, a virtual photon, this actually leading term in the power counting compared to exchange of two partons. Then luckily, this could be smaller because by exchange high power like electromagnetic coupling constant. Then so this is exactly the struggle JLab folks have to try to separate the DVCS measurement from the extraction of the GPD. Then for this exchange of heavy quark pair, not heavy quark, light quark pair, or the gluon pair, you can easily convince yourself of pulling two particles in the same direction with a different scale. This is a very short distance scale. This is a relatively long distance scale. You pay a penalty, the ratio of those two scales. So the overall scale, this contribution to the cross-section from this channel is actually power suppressed compared to this channel. But advantage is, of course, you don't have an extra power alpha yet. Now, what happened? Okay, so I think I have to move this a little bit. Okay, so the question is, now, can we factorize it? Oops. So this is sort of, we discussed the minimum condition, new type of process. Can we really factorize it? So the answer is yes, under certain condition. So then I show you a fact for the QCD. In QCD, we all know any scattering cross-section with identified hadron cannot be calculated fully in QCD perturbation theory because it's a hadronic scale involving identified hadrons. But luckily, QCD factorization is a controllable approximation in some sense with the three major features you have to satisfy. Number one, all the process-dependent non-perturbative condition or contribution to the cross-section better to be power suppressed. They be thrown away if the Q square is large enough. Then all factorizable non-perturbative contribution should be process independent. So you can have a universality of PDF, universality correlation function. You can test them through different measurement. If they become the process dependent, you cannot predict them. So third one is that all the process dependence, if you can calculate, has to be perturbative calculable. Otherwise, you don't have predictive power, or you could not distinguish between different observables. So those three things have to be satisfied. Then what the predictive power? Predictive power actually follow when the cross-section with different Hall scattering, but same long-distance non-perturbative physics are compared. So that's exactly we know we to compare PDF. That's a simple example, but here I'm dealing with the GPD or even other observables. So the challenge is, it's not simple because what we're going to effectively want to prove is have a diffractive process along with a very short distance Hall process, but because the hadron involved, you can have a soft gluon all over to connect them. Goal is I'm going to factorize it in such a way there is a simple clean GPD multiply a short distance probe, which you can calculate perturbatively. That's a goal. So before I do, to save time, I gave you, I'm not going to through all the detail, but at least to give you a flavor what's involved. So we remind everybody what we did, is, like Keith talked about Joy-Yang. Took people over 20 years to finally prove Joy-Yang cross-section at the leading power can be factorized. The next leading power can be factorized later, but beyond that, you cannot factorize it. Joy-Yang cross-section as a whole is not factorizable. So the idea is, as Libby and Stephen Libby and George Sturman, long time ago, leading contribution from all the high-order process can be organized into three regions. One is so-called hard, one L the line offshore by the Hall scale, one is the collinear, when they collinear to the hadron incoming or colliding, in this Joy-Yang case, the colliding hadron, then then soft. Soft is the one gave you the trouble. Hard collinear one is easy because they're longitudinally polarized. You can apply water entity, get converted, detached from hard power, put it into the gauge link. This is exactly what the Ian talked about the soft collinear effective theory is the gauge link over to go along with the active proton to make the things gauge invariant. Then the harder one is the soft factors. Because you have spectator, two hadron come in, you can have a soft interaction between them. For a simple example, I have a gluon attached to these two but the momentum have to circle back, then you will immediately realize this momentum were against the direction of this momentum and along the direction of this active proton, these two will give you the exact pinch singularities. What that means you pinch your plus component and soft minus component of your soft gluon to be an order in terms of power less than the transverse component. So you are forced into so-called global region. The plus component is much smaller than transverse component. When you contract it with a larger momentum from the active proton, then you realize the transverse components start to contribute. So you cannot factorize these soft things from the spectator, then the factorization completely broken. Luckily, took 20 years, pioneered didn't work. They tried to sum over all the hadronic final state. Because we don't observe them, we only observe Joy-Yang. Sum over all the hadronic final state. Unitarity tell you the pole in the one-half plane completely canceled. So at the end of the day, the pole are not pinched anymore. You can deform your contour. Eventually, you end up with a factorized formula. They immediately realize there's a problem for the exclusive process. because I try to prove factorization for exclusive process. If I have this kind of pinch singularity, I have no final state to sum. I have only one well-defined final state for the exclusive process. So then what the difficulty is that for this, I gave you one particular example, say this 2 to 3 exclusive process have a pion scattering to the proton with the proton diffracted. Then in this case, I have 2 photon final state. So make life a little bit simpler. So only 2 hadrons involved, plus 1 diffracted in this case. So there are 2 regions, so-called ERBL region with the 2 exchange quark moving in the same direction. So in this case, you can treat this almost like a virtual quark, a virtual pion interacting with another pion, goes to 2 photons. It's a half scale, single half scale problem. There is no pinch. Perfect, fine. But there is a problem. There is a deglab region. Deglab region means only one active proton participates in hard interaction. Then the proton come out of hard interaction, merged with this rest of spectator, become the hadron you observe. In that case, this diagram very much like a Joy-Yang diagram. Then you realize immediately if you do this gluon, then these 2 lines will be pinched. Pinch singularity. Then because this is a final state, you can also route your momentum this way, but you will find the exact same pinch. Nowhere to escape. But luckily, for this process, I only interested on the single hadron diffracted. So what happened, if the hadron moves in the plus direction, minus component is pinched, but the plus component is not pinched like a Joy-Yang. So I can deform my contour, actually, in such a way to move it away from that. So that gave me a chance to factorize it. I use slide to argue that. That also gave me a chance to answer the question people had for more than 20 years ago. So then the basic step to prove it, if you have this diffracted, is that they have dressed up the gluon for the initial 2 different regions. The key is that the longitudinal collinear gluon is easy. I don't mention it here, but it's a soft gluon. Soft gluon, normally we handle by unitarity inclusive process. By exclusive, actually the cancellation, say soft gluon attaches pion, because the fact the pion is color singling. So the gluon actually canceled. The difficulty is the plus component is not pinched, so I deformed into the larger scale and changed this soft gluon in the global region, end up with like the collinear proton. They worked like one of the initial proton, so end up with this part as a GPD, then this part is a hard process. So that's factorization can be achieved. Because of this, you immediately realize double diffractive process will not factorize, will not be factorized, even you have large momentum transfer. So this is exactly what Dave Soper said in 1997. There is a little bit historic event. Harold find the diffractive distribution. People apply that to the Tevatron. You have 2 diffractive distribution to predict the jet cross section. The prediction was order magnitude away from the data. Then recall Dave Soper mentioned in one of the CTAC meeting, factorization have a problem. But in my backup slides, you can see just one slide. You can immediately prove that will not work. So now with this factorized, we'll go back to DVCS. So all this process can be put in exactly this framework. Like a DVCS, you can have 2, in the sense I say my hadron H is a proton, H prime the proton, colliding beam in this case is electron, scatter C is electron, another one is the photon. This combination is exactly DVCS. Then you have 2 different regions, can be factorized in this form, but you can calculate matrix element, end up with a short distance kernel, have unpinched pole from this diagram. That exactly tells you the X integration is not sensitive to external measured half scale QT and a Q square. So it's a completely dummy variable integrate over around the size value of the Kc. So if imagine you fix the T and the Kc, you want to see the whole range of X dependence, no way, you don't see that from this measurement. So what happened? How can we invent a new observable which give you the chance to see this kind of dependence? A simplest one is the so-called double DVCS. Because of You want to, instead of measure a real photon, measure a virtual photon decay to the dilepton pair, because the virtuality of this line depends on the scale of this virtuality. So the x minus this quantity is not the c, actually depend on this q square. If the q square goes to 0, of course, go back to c. But if you measure this q square, you will be able to see different effectively different value of x, have different sensitivity on the x. But problem is the double DVCS, you have another 2 power of RFEM. Becomes very, very small cross sections. Only chance to measure probably JLab, but EIC won't be able to measure. Yeah, so then my collaborator and I propose a new class additional process. The process is that you look for 2 particle high PT. So the transverse momentum particle you observed have to go through the collision, goes to other hadron you observe. But if that flow of transverse momentum entangled with the relative momentum of the pair, that's x. The example I show here is example, if I look for 2 photon final state, the PT had to flow here through this gluon and coming back to other photon you observe in the final state. This momentum flow will entangle with this relative momentum x. Because the entanglement, by changing the PT, it becomes sensitive to different value of x of your GPD. So that's exactly what we proposed. They measure the cross-section, a differential cross-section, a function of a PT of the photon, then you can measure different range of a value of the GPD. So give you a specific example, numerical test. So I invent a GPD based on people have been used for white paper, this thing called GK model with all this reference. So I'm going to make x dependent as simple as possible. Then in that case, you can imagine the x dependent is nothing but x rho 1 minus beta. But I choose different variable rho and tau in this case, I have my x dependent of GPD all over the space. I want to see whether or not this new observable will be able to tell the difference. So I take the observable, exact 2 photon final state with this distribution. You can see the cross-section at the J-Park energy. I talked to their experimental colleagues, they're actually interested to measure it. You can see the difference. So the measurement of the PT dependence will help you to separate the X dependence. So furthermore, even more direct observable to my home, JLab. Because JLab is unique, have photon beam. The photon beam, not only the beam, but also has polarization. So what we did is say we propose a crossing process. Say the photon collide with a proton, look for the pion and the photon final state. But large PT, important. So then you will find the convolution of this X at an amplitude level it's not a simple Cassie like a DVCS, rather a dependence of angle, which angle is of course related to the PT. So they are very sensitive to the so-called ERBL region. I didn't say detail for other process, I mentioned crossing process is very sensitive to DGLAP region. So these 2 processes is really complementary. So now I invent not only say a single measurement of cross-section, because the JLab, not only the beam can be polarized, target can be polarized too. So I can invent an observable in this measurement, have a scattering of a proton coming deflected a little bit, a photon beam coming to collide. So this defines my scattering plane, or as I say, diffractive plane. But 2 particles come out back to back. That defining the scattering plane. The angle modulation between these 2 planes depends on the quantum number of the exchange state, spin. So what happens is I can construct a cross-section at this phi, astrometric angle dependence, in terms of different asymmetries, of course, multiply the total cross-section. Then in that case, we can construct a different asymmetry corresponding to different matrix element, depend on different GPDs. So I gave you some example now. Remember I say I can construct the GPD, based on the GPD, fit the DVCS data. I add another term, so shadow GPD. I can construct a shadow GPD, have very wide structure, but does not contribute to this moment. and it does not contribute to forward limit, because forward limit is controlled by PDF. With that, so I can use this distribution to calculate my prediction. You will find the cross-section, asymmetry. You can see this is all over. That means the measurement gave me a chance to really extract the X dependence of GPT. So then, and also exclusive process, we can do different energy. Imagine last one I used the 9 GeV, the current energy. If we increase JLab energy a little bit, so then you will have, again, the symmetry. But the most interesting thing is I can plot this as a function of root S from the energy I have now to whatever beginning of the EIC. You see the feature, which is completely understandable. For inclusive cross-section, when you go to EIC, high energy, you open up more phase space, and the flux, platonic flux, gluon goes crazy, so you have more events. But for exclusive process, you actually have penalty. Because you're pulling the pi in the same during a high PT, instead of a single proton, when you go to high energy, you pay a penalty. It's like high twist. So in exclusive process, in the language inclusive process, is typically the high twist process. So when you go to high energy, actually does not buy you more cross-section, actually going down. So there is a sweet spot to do this kind exclusive process, look for the internal structure of hadrons. So if we do that, we really have a chance eventually to measure this kind of three-dimensional structure of the hadrons. So I use the last minute, a few minutes, to explain a collaboration. It's supported by DOE known as SciDec collaboration. The collaboration we call the quantum collaboration involving the Argonne National Lab, JLab, and Virginia Tech. Then we have, it's a SciDec is supported by both nuclear physics and OSCA in the DOE. We have both people from FastMath and the Rapids Institutes. Then the basic idea is following. Instead, I'm going to build a Monte Carlo event generator. I do opposite. When you build an event generator, we heard the other day, then you start with the make approximation, how to handle the shower, then how to handle hadronization. Here, I'm going to limit myself to a simple observable. I start with a theory I believe under control, say inclusive DIS, semi-inclusive DIS, or certain exclusive process. So far, we concentrate 3 types of observable. The final stage is 1 particle inclusive, 2 particle inclusive, and 3 particle exclusive. So I start with a factorization formula where the only unknown is the PDF, for example, or TMD. Then I use a Monte Carlo generator to generate all kinds of replicas. So in the sense, I generate many, many templates from the correlation functions for the trust theory within that kinematic region. Then when I have data coming real time, read out, you can see the emergence. We have many replicas like LIGOs do, but emerges which one is the correct one. See the proton structure coming out, or PDF come out of that. Then that's step 1. Step 2, I expand my kinematic region. For example, I go to low Q square where the factorization formula start to break, what I learn. I go to small X region, like Roger mentioned it, see what I learn. But data is data. Data is there. I'm not going to massage data, change the data. I take the data, put in either 1 particle inclusive, 2 particle inclusive, either or exclusive. That's for structure. So in that case, the workflow we have, as explained here, because to extract this information from a cross-section is over the inverse problem. Then how you handle that effectively, so we would, instead of waiting for our experiment colleague, bring in the data, get to the point, theories come back to do global fitting, to extract some PDF. No, we work together with experiment. We start from theory event, then with experiment, for each given detector, they can have use the machine learning to simulate the matching, then eventually compare at the real event level. So that's a project, so let me finish it. So I say this single diffractive high exclusive process really provides a reliable way to explore the tomography of nuclei without breaking them. And also extracting their X dependence is extremely important. Not only the GPT itself, their moment, directed conductor, emerging property of the hadrons. And the 50 years of QCD established as the right theory, we learned a lot. Many challenges and open questions remain. But I want to emphasize again the region of the so-called femtoscale, QCD, the femtoscale between 0.1 Fermi to 10 Fermi, the total order magnitude, is the most interesting, rich, and complex region of the theory, at least for the phenomenology. Then finally, I would like to thank all the pioneers who discovered QCD and the methods allowing us to explore the QCD now. I would like to thank Al Miller, who is my advisor, who introduced me to the QCD because I started as an experimenter in astrophysics. So that was a great help to get me interested in it, and especially George Sturman, who is my mentor and a collaborator. He introduced me to the factorization, the predictive power. He always emphasized what is the predictive power. I think that's very, very important. I'd like to thank the organizer for organizing such a nice historical event and an opportunity to speak and clap to celebrate the 50 years of the QCD with all of you. Thank you.
What are we going to celebrate when we're all here at the 75th anniversary? In particular, plans for a muon collider in the Rick Ring.
For the muon collider, if you can convince a politician in the U.S. to build it.
I was asking more about the scientific interest. And pushing much lower X with 800 Jeff muon.
Yes, yes. Yeah, muon collider, in the sense, it's a collider, high energy E plus minus mission to really help understand the QCD dynamics through what you produce. So it's a slightly different what I say here. What I say is try to really understand structure. But there is another part of QCD is from the emergence of hadron. Here is the structure, confine the structure of hadron. Then the emergence of hadron, once you produce a proton, it becomes how the hadron come out. That's a hadronization, which is very different, not even lattice calculation. Shantou mentioned try to calculate. Hadronization you cannot calculate. So that if we do that from QCD point of view, you provide another huge laboratory for us to understand, especially the jets of the footprint of the high energy proton, but jet internal substructure, which tells you how QCD work, then how the hadron come out of it.
But you'll go down much lower in X, right?
No.
No?
Say it again. That's a different initial use for muon. Then it's not the X I'm talking about. For muon collider is the final state. It's a muon. Muon. I'm sorry. I'm sorry. My mind is stuck. Yes, it's like an early CERN experiment, that like NMC or they have muon beam on the hadron. Yeah. Yeah. Yeah, yeah, yeah.
Because the EIC is going to run for another.
Nevertheless, it will go down much lower in X.
Correct. And also help in terms of radiation correction. You probably noticed in my paper recently on how the impact of the QED radiation in the lepton hadron collider. Yeah, that's actually a huge impact because, yeah, go ahead.
Comment. I mean, there's a somewhat more realistic proposal, relatively speaking, of putting in an electron beam at the LHC, which you know about. It's called a Large Hadron Electron Collider. And that would go to really low X of 10 to the minus 6 at large Q squared. But its future remains. But it's on a shorter time scale than, say, muon ion collider.
That's correct. That if I use official words we use in the EIC white paper, then EIC US version is in the sort of sweet spot, the transition part. But if you go to very, very deep saturated region, if there's a flatten out, then it's like a Ricky in the really transition part, phase transition part. If you go to LHC, you see a lot of phenomena, but may not be as sensitive to the transition of that.
Why don't we go to this question on Zoom?
Sure.
Jeff Bodman, unmute yourself.
Hi, Jeff.
Hi, Jianwei. When you discussed factorization for exclusive diffractive production in the DGLAP region, you mentioned that there's a pinch in one of the light cone variables.
Correct.
And that's a situation that was encountered a long time ago in the Drell-Yan process for active spectator interactions. And there the solution was to deform the contour for the free light cone variable out of the Glauber region and into the collinear region. And then the contribution could be recognized as a part of a Wilson line that could be incorporated into the parton distributions. Is that the same sort of solution that you have in this?
Yeah, exactly. That also tells me the double diffractor will not work.
Mm-hmm. Okay. Okay, thank you.
It's great, all the processes you're talking about and so on. But of course, I can't resist saying that we could use light front holography to make really remarkable predictions for virtually all the processes. It's got confinement and specific models for the distribution amplitude, the valence, light front wave functions. So it's a fantastic testing place of all the things you proposed. And it's really, a remarkable, rigorous feature of the ADS-QCD CFT correspondence.
This kind of observer can open up the more opportunity.
Absolutely.
Yeah.
One more question. Before QCD, showing how old I am, we often thought of the proton as being having a pion cloud around it. It sounds a lot like what you're doing is trying to probe the gluon cloud with a hard scattering off of the cloud. Is that part of what you're doing?
Yeah, we can, in principle, because once you go into actually it's said in EIC white paper, if you can really precisely probe the probability to find the quarks gluon at the 1.2 or 1 Fermi, that's exactly where the cloud is. Yeah.
Let's